Okay. Uh, Today I want to talk about applications of the cup product. Well, there are lots of those, and let's consider a couple. There are uh, what people call division algebras, and there's that can be defined over arbitrary fields. And just to recall what it is, it's a vector space over K. Equipped with a bilinear product let's call it mu, such that for all x, well, let me let me use a different character here. So for all x non-zero, uh, the maps given by multiplication by a fixed non-zero element x are isomorphisms. Uh, well, for k equal r, there are classical examples. And there are Uh, there are other examples both over R and over other fields. In fact, uh, despite the fact that there are many examples, the dimension uh, of a division algebra over R cannot be arbitrary. There's 1, 2, 4, and 8, which are all possible as dimensions of division algebras, and in fact, this is all there is. The dimension of division algebra over R it belongs to this set. Uh, and there's there is a topological proof of this, and to my knowledge, there is uh, uh, there is no purely algebraic proof when one doesn't assume something about the division algebra. Uh, for example, if one assumes that the algebra is associative and commutative, then there's an algebraic proof that the only options are R and C. Likewise, if we assume associativity, then there's an algebraic proof that one gets one extra possibility H, the quaternions. However, if one doesn't assume anything, then basically algebraic methods sort of become more complicated, and the only proof I know is topological. Well, there are several proofs to be more precise, and those use techniques which we haven't covered yet. So let's prove a weaker statement. We'll take k equal r. Namely, let's prove that the dimension of a division algebra over R is a power of 2. So well, let's take a division algebra, and the first observation is that we may assume that uh, the algebra has a strict two-sided unit or identity. Which means mu x comma e is mu e comma x is x for all x in V. The well, this is a purely algebraic fact, which basically consists in replacing the product in the algebra with a different product, uh, which has a strict two-sided identity, which can be chosen to be any non-zero element uh, of of the underlying vector space. Well, let's denote the dimension of V by n plus one. Uh, since mu is assumed bilinear, we we get a well-defined continuous map, which I denote mu from RPN cross RPN to RPN. Wait, does this make sense?
Yeah, it makes sense, but it's not very obvious to me that the two-sided identity exists.
Well, I don't remember how to modify the formula. Let me try to let me try to remember this during the break, and then I'll write down the formula, and once the formula is there, it's straightforward to check that get an algebra with a strict identity. Now we use cohomology. And we will we will see later today that the cohomology of RPN with coefficients in Z by 2 is the polynomial ring on one generator of degree 1, quotiented by the relation the generator to n plus 1 equals 0. Now, Z by 2 is a field. So using the Gorinov theorem from last time, we get a formula for the cohomology of RPN cross RPN. And the answer is we need to take the product, the tensor product of the two cohomology rings, and and we simply get the polynomial ring on two generators, A1, A2, quotiented by the relations A1 to the n plus 1 equal A2 to the n plus 1 equals 0.
And I want to make sure that here the tensor product is over Z over 2, right?
Yes, tensor product is over z by 2 or over z, which is the same in this particular case. When we tensor multiply two truncated polynomial rings, we get another truncated polynomial rings with the same variables and basically the same truncations. Okay. Now, my next claim is new upper star of A is A1 plus A2, where nu is the map induced by the product. Why? Well, because we have a two-sided identity. So we can write nu upper star of A is equal to k A1 plus L A2 and then we restrict to E cross RPN and RPN cross E. And the result is that k equal L equal 1. Wait, does this make sense?
Yes.
Okay, then we remember that a to the n plus 1 is 0. So a1 plus a2 to the n plus 1 is also 0. And then we use the binomial formula. A1 to the n plus 1 plus n plus 1 A1 to the n A2 plus etc. plus a2 to the n plus 1. And this follows from the binomial formula. Well, the first and last terms are zero by the relations in the cohomology algebra. But there are also lots of terms in between. And my claim is at least one of the binomial coefficients is non-zero unless n plus 1 is a power of 2. So in other words, if n plus 1 is not a power of 2, then one of the binomial coefficients in n plus 1, choose n plus 1k, is non-zero mod 2, which is an exercise in basic number theory. Wait, does this make sense?
Yes.
On the other hand, if n plus 1 is a power of 2, then all the intermediate binomial coefficients are 0, and this is why the Frobenius endomorphism works in characteristic 2. Okay. Are there any questions? Wait, are there any questions?
No, I'm still thinking about how to prove this exercise in number series. So others is okay.
Okay. Well, let's just postpone this until after the break. It's not particularly related to algebraic topology. Now let's see an application to homotopy groups. Well, let's define the Hopf variant. Suppose we have a map from S to M minus 1 to Sm, continuous map. Now, my claim is the cone of F is a CW complex with cells of dimension 0 to M, 0, M, and 2M. Now, let's see if this makes sense. Does the cone of F make sense?
Please recall it. I forgot how we define this.
Okay. So. Well, suppose we have a continuous map from X to Y, then we we can form we can firstly form the cylinder of F. As follows, we take the disjoint union X cross 0, 1 and Y, and we attach we attach the bottom of X cross 0, 1 to Y along the map F. And then we can define the code. we can define the cone. By collapsing the top of x cross 0, 1 to a single point. So the cylinder is a top hat, and the cone is a wizard's hat. Does this make sense?
One question: the operation by of attaching y to, I mean, for constructing the cylinder, the operation of attaching y to x cross I is, I don't get it. How we attach y here?
Okay, so in more detail, we'll take x cross 0, 1, just joined with y by the equivalence relation x cross 0 is equivalent to f of x for all x in x.
Okay, thanks.
And then we identify, we collapse the top part of the cylinder, and we get the cone. Okay, so now we understand what a cone is. Now my claim is we we have a CW structure on the cone of any continuous map from S to m-1 to Sm, and the result is a CW complex with 3 cells, and the dimensions of these are 0, m, 2m. The cone of F contains the target space. The target space is Sm, and the cells of dimensions 0 and m are the cells of the standard CW structure on Sm. And then we get just one extra cell obtained from the source sphere. Does this make sense?
Yes.
So the cohomology of the cone has z's in degrees 0, m, 2m, let's choose generators, additive generators of those z's in degrees m and 2m, and denote them a and b. And for general reasons, a squared will be a multiple, an integral multiple of b. And the coefficient of a squared is called the Hopf invariant of f. Well, the first observation, this really is an invariant. It's well defined because the cone the homot of the type of the cone depends only on the homot of the class of f. And well, well, there is still an ambiguity If we replace b with minus b, then h will change sign, but otherwise it's well defined. Well, the next remark is h the the H is a group homomorphism. Before we discuss this, let's observe that if M is odd, then H of F is 0 for every F S to minus 1 to S M. Why? Well, the degree of A is M. So A comma A is minus 1 to the M squared, which is minus 1, A comma A. So A squared has additive order 2. But in Z, there aren't any non-zero elements of order 2, which means a squared must be 0. So the only the only interesting case is when M is even. Okay. Well, now let's see why the Hopf invariant is additive. On the right, we have the sum of two integer numbers. So it's pretty clear what we mean by this. And again, the formula is same as the first observation. In order for this to work, we need to fix B. not A. A is also defined up to sign, but squaring A eliminates the sign. But we need to have we need to choose B in some way, and well, let's just assume we choose any of the two possible generators and proceed. Okay. Now the right-hand side is clear. It's just a sum of two integers. What about the left-hand side? Does the plus sign in the left-hand side make any sense? Wait.
Actually, no.
Okay. Well, let's recall. Let's briefly recall what the homotopy groups are. Suppose we have a base space, meaning a space with a base point. And then we can form we can take the set of all based homotopy classes of based maps from Sn to X. And this is a group. So suppose I have F Sn to X, and also G Sn to X. Then I define F plus G as the class of as the class of the following map. We take a sen and collapse the equator. And let's assume that the base point is on the equator. And what do? We then define the map as f on the first copy and as G on the second copy, and we get a well-defined map, and the well, let's assume that n is greater than or equal to 1 for n equals 0. This doesn't quite work, but for n for n equal 1 it does work, and for higher n's as well, and we get a group which generalizes the fundamental group. And this group is moreover abelian if n is greater than or equal to. And as a side remark, the set of based homotopy classes of maps from a suspension to any space is a group, and this group is abelian if we take maps from a double suspension. Well, the spheres are suspensions starting from S1 and double suspensions starting from S2. So this is consistent with what we've just seen. Does this make sense?
Yes.
Okay. Now, the homotopy groups are quite a bit harder to calculate than the homology groups, which and there is a reason for this, but let's not get distracted. Well, now we understand what the left-hand side of the formula on top of page 5 means, don't we? Wait.
Yes.
Okay. Well, let's see why this is true. Uh, okay. Well, to begin with, let's form the let's form the union of the two cones, and let's call the result X. Where by the union we mean we glue the cones along SM. Both cones, the cone of anything contains the source space, and we just take the disjoint union and identify the copies of the source space. And the result will be a CW complex with cells of degree 0, M, and 2 cells of dimension 2M. which is which is just a consequence of the fact that we glue together two CW complexes along a subcomplex of each.
Then shouldn't we have also two cells of dimension 0?
No, because the cells of dimension 0 are inside SM, and they are identified. And the same applies to the cells of dimension M, but not to M.
Oh, okay.
So A squared is H of F A1 plus H of G, B1, H of G, B2. And then my claim is the cone of F plus G maps into X, and the map commutes with the inclusions of SM in the cone and in X. Now, how to construct this map? Well, the map works as follows. Sorry, not X. We have F plus G, which is a map from the sphere S to M minus 1 to SM, and by construction it factorizes through a map from the wedge of two copies of Sm plus 1. And so we have a map from cone F plus, well, let's call this map F wedge G, cone of, so we get a map from cone of F plus G to cone of F wedge G, and the cone of F wedge G is homotope equivalent to X. Why? Well, let's try to draw this. Okay, let's try to draw this on the next page. Let's try to draw this on the next page. So we have cone of F, the cone of G, and then we can inside each cone we have a line segment from the vertex of the cone to the base point of Sm, and when we collapse, we don't actually collapse. We identify the two segments as shown in this picture, and we get the cone of F wedge G. So the result is we have the cone of F plus G, which maps into the cone of F wedge G, and my claim is well, let's call this map B. Well, the copy of Sm is the same for all cones. Nothing happens to it. So P upper star of A is A. And the next observation is P upper star of B, 1, and the same for B2 is B. And combining all this, we see that in the cohomology of the cone F plus G, we have a squared equal to B, but this time the coefficient will be h of f plus h of g. Okay, well, we need to have a break soon. Are there any questions?
No, it's clear.
Okay, then let's have a break and pause the recording, and then we'll finish this example. The purpose of this example is to show that that pi. So we want to show what do we want to show? We want to show that pi pi 2n, no, 4n minus 1 of s to n contains z. So, in other words, the group pi 4n minus 1 of s to n is contains an isomorphic copy of z, and this is the only non-trivial example of a homotopy group of a sphere, which is infinite. We have pi n of Sn isomorphic to Z. Well, this is sort of well, it's very important, but it's sort of intuitively clear. But there is one more example when the group is infinite, and this is pi 4n minus 1 of S to n. and all other homotopy groups of spheres are finite. I will say something about it after the break. Okay, let me see. Pause recording. Yes, thanks. I've forgotten to turn on the recording. Anyway, yeah. So we've just what have we just done? We've just constructed maps, lots of them, with Hopf invariant 2, and we said that maps with Hopf invariant 1 do exist, but they are relatively rare, and this is all related to the structure of to the existence of a structure of a division algebra over R. Okay. Now we need to say something about the Poincare duality, because we actually sort of use it today. Well, for example, the easiest way to prove this this isomorphism would be to use the Poincare duality. So let's say something about it. Well, to begin with, let's consider a particular case, and maybe later we'll cover some generalizations. So we start with a compact topological manifold without boundary. Now, does every word in this phrase make sense?
Me, yes.
Yes, sir.
Okay. Now, let's denote the dimension of M by N. We say that M is orientable if there exists a class mu in Hn of M with let me make a slightly more general definition. Let me choose a commutative ring and say that M is R orientable if and only if there exists a class mu in Hn of M with coefficients in R, such that mu restricted to the couple M minus X and this restriction lives in Hn M comma M minus X R. And this group is isomorphic to Hn Dn S n minus 1 R, and this is isomorphic to R. And the condition is that the result should be a free R generator. No, there are basically two cases. If R has characteristic 0, no, sorry, characteristic 2, then every M as above, meaning compact topological manifold without boundary, is orientable, is R orientable. Otherwise, M is R orientable if and only if M is Z orientable. Which is equivalent to saying that Hn of M is R, and assuming M smooth, this is equivalent to orientability in the usual sense. Of differential topology. Meaning we have we have a local tangent frame at each point such that all transition maps have positive determinant. Okay, so as a result, we know plenty of examples of orientable and non-orientable manifolds. For example, the sphere Sn is orientable y because Hn Sn is isomorphic to Z. Well, for the same reason, Tn is orientable, the n-torus and by the Gorinov formula, if M and N are orientable, then so is the product M cross N. And RP2 is not orientable. Why not? Well, well, there's lots of ways to prove this, but one particular one would be to calculate H2. And what is H2 of RP2?
Over two.
Say again?
Z over 2.
No.
No.
The answer is 0. Why? Well, this is something we calculated in week 1 or in week 2, but let's let's briefly revise this using, for example, cellular chains. The cellular chain complex of RPN is given by this formula. There are z's in all degrees from 0 up to n, and the differentials are 0 and 2 alternately. And this, well, this is something something that's probably in the problem sheets. So I do encourage everyone to try to prove it on their own. As a result, for RP2, we get z by 2 in degree 1, and we get 0 in degree 2. More generally, RPN is orientable. If and only if what? When is RPN orientable? Well, RP1. What about RP1? Is RP1 orientable?
And only if n is odd. RP1 should be, yeah, RP1 is orientable.
Yes. And if n is even?
If even is top homology is C over 2. No, it's 0. It's 0.
Yes. The condition is n is odd. RPN is orientable if and only if n is odd, which can be seen by looking at the cellular chain complex, which gives one the homology of RPN. CPN is orientable. More generally, every complex analytic manifold is orientable. Well, what else? I think we have enough examples to convince ourselves that well, there are plenty of orientable manifolds and plenty of non-orientable manifolds. So the Poincare duality theorem. suppose we have a compact topological manifold without boundary. If M is R-orientable, HIM with coefficients in R is isomorphic to Hn minus I of M with coefficients in R, where N is the dimension of M. Well, what else? Well, we need to construct an isomorphism. But before we do that, let's consider an example. Let's take M equal RP3. Let's calculate the homology of RP3. And let's take R equals Z. What is the zeroth homology of RP3? Can anyone tell me by looking at the cellular chain complex above on the same page? Anik, what is the zeroth homology of RP3? Wait, can you help, Anik?
It's T, and in degree 0 and 3, we have T. In degree 1 and 2, we have T over 2.
Yes, so we have Z by 2. Now, in degree 2, we have what?
It will be Z, right? Actually, sorry, I was writing the stuff. It will be Z, zeroth homology group of RP3.
Yes, yes. The zeroth homology group of RP3 is Z, then Z by 2, and then what?
And 0, I'm sorry.
The second one is 0, and the third one is what?
Z again, because it's orientable.
And the third one is Z. Okay, so what about cohomology? for cohomology, we have the same cellular chain complex, except all arrows get reversed. So what do we get in degree 0?
We get by configurator, we just write the previous sequence.
Well, let's not use Poincare duality. Let's just calculate the answer using cellular chains and co-chains just to convince ourselves that the answer is consistent with the Poincare duality.
It will be R, right?
In general, H0 is the functions from the set of path components to R, but in this particular case we have R equals Z, and the space is path connected, so we have Z, which can also be seen from the cellular co-chain complex. Now, what about the first group? The first cohomology group. What do I have?
0.
Yes, the first one is 0. What about the second one? Well, the second one, okay, let me cellular chains. Z0, Z2, Z0.
It will be Z2.
Yes. Cellular co-chains, same groups, same differentials, arrows reverse. So in degree 2, I have co-cycles which are Z. The co-cycles is the whole Z because the differential is 0, and but the co-boundary is 2Z inside Z. So the quotient is Z by 2. And the final group is what? Well, let's look at this.
Analyze that.
This complex. The whole Z goes to 0 under the differential, so the co-cycles are Z, and the co-boundaries, well, the co-boundaries are 0 because the previous differential is 0. So the answer is Z. And as we can see in this example, the answer agrees with the Poincare duality. And in fact, both arrows in in the Poincare isomorphism from the previous page can be given by explicit formulae. Well, the in one direction, the construction is slightly easier than in the other direction. So let's start with let's start with the first one. And to construct this this thing, we need the cat product, which is well, which is something similar to the cup product, except it involves homology and cohomology at the same time. Now let's see. So let's give a definition for an arbitrary topological space. We don't need manifolds in this in order for this to work. So we want to construct the cat product on the level of chains and cochains. So we have the cat product map. Given as follows. Suppose we have a singular simplex sigma, an L cochain phi. Then what do? We take this couple sigma phi to phi applied to the front K face of sigma times the back K minus L face of sigma. Okay, now let's look at this expression and see whether or not it makes any sense whatsoever. Wei and Nick, does this expression make any sense?
Yes, sir.
Yes.
It's fine.
Okay, now and as a result, we get a bilinear map CK X cross CL X K minus L X R, and the and by passing to the tensor product, we get a map of complexes very well. Now the statement the bit of complexes is not entirely for free because it involves the Leibniz formula. And the Leibniz formula is as follows: delta sigma cap phi is minus 1 to the Lth delta sigma cap phi minus sigma cap delta phi. I don't want to check this formula because it's not really illuminating. But let's keep in mind that this formula is there. And this can be checked by a direct calculation. And there are a few more things which can be checked by direct calculation, and these are sigma cap 1 is sigma for all sigma, and sigma cap phi cap psi is the same as sigma cap phi cop psi for all sigma. And for all for all phi and for all psi. Now, Anik and wait, do these formulae make any sense?
Yes.
Yes, sir. It's okay.
So this makes C lower star x comma r into a right digimodule over C upper star x comma r. Basically, the sentence C lower star is a right digimodule of C upper star is exactly what we have just written using formulae. Namely, we have the Leibniz formula, and we have these. Okay, let me underline those formulae. And the three formulae, a shorter way to express what these three formulae say would be to say that C lower star is a right digimodule. And these two formulae are again checked by direct calculation, which is actually easier than the Leibniz formula. Now, there's one other thing which I need to mention, namely, we need to understand how the cap product behaves with respect to continuous maps. Now, suppose we have a singular case simplex of x and phi a singular L chain of y. Then we have then we have
Do you mean phi is a cochain here?
sorry, co-chain. Yes, thank you. Phi is a singular co-chain. What does this formula? So this is the projection formula. What does this formula mean? F induces a map of rings. So C lower star of x is not only a C of x module, is also a C of Y module. The projection formula says that the map F lower hash from C lower star to C lower star is a map of C upper star of Y modules. This is all the projection formula says. Okay, are there any questions? I suggest we finish now, and then the day after tomorrow, on Monday, I will review all this and explain that we have as a result of these facts for chains and co-chains, we have the same sort of results for homology and cohomology. Okay, are there any questions, remarks, comments, criticism? Okay, well, it looks like there aren't any of these. So let's call it today, and we will meet again on Monday in the math department.
Sir,
yes.
actually, I was wondering how will you conduct the exam?
Well, do you think you will be able to come to Moscow for the exam? Let's be realistic. Is it likely, unlikely, or something in between? Anik. Anik, can you hear me? Well, Anik has left the building. Okay, Wei, you're probably not interested in taking the exam, so the question is mute.
Yes. So.
Okay. Okay. Well, then this is it for today, and we'll see each other probably next week on Monday.
Okay. Goodbye and see you.
Bye.